So you might wonder why I'm giving an astrophysics talk in this meeting, but I will make that clear as we go along. So you have the title of my talk. First, acknowledgements. This work was done with Akhilesh, my student, and Mark Brachet. Akhilesh is now a postdoc in Warwick, and Mark is at the École Normale in Paris. I acknowledge support from these funding agencies, especially the Indo-French Center for Applied Mathematics. Here's an outline of my talk: felicitations, motivation, the Gros-Pitayevsky-Poisson equation, and with a crust, and then our results. So first, felicitations. I have had the good fortune of knowing Mustansir and Deepak for close to 40 years now. My best wishes to them. Congratulations on their inspiring academic journey, and we look forward to following your exciting research for many more years. And we also give your families our best wishes. A wonderful performance. Thank you very much. So I go back to an old problem. In 1969, two papers appeared back to back in Nature. The first was by Radhakrishnan and Manchester, and the other by Rachley and Downs. Some of you might remember Professor Radhakrishnan, who then came back to India and served as the director of Raman Research Institute for several years. So what is it that they were finding? They found that the pulsation period of a given pulsar is known to increase gradually, but between two dates, the periodicity abruptly decreased by 2 parts per million. And this is the original plot. You don't worry about the axes just now in the Radhakrishnan and Manchester paper. I mean, many of you might remember Professor Radhakrishnan, So about 50 years after that, there is a paper by Manchester on pulsar glitches, first observed in 69, and now, at least in this year, which was 2018, 520 glitches are known in more than 180 pulsars. So what can a poor statistical physicist say about such an astrophysically hard problem? Well, it has been known for a long time that neutron-Cooper pairs comprise a major component of the nuclear matter in a pulsar, and they form a superfluid. So of late, since about 2012, there has been some effort to model this superfluidity by using the Gros-Pitayevsky equation, and in addition to include an externally imposed potential or container and a pinning potential for the crust. Similar models have been done in 3 dimensions, but so far it has not been emphasized, well, people know, but they haven't done it, that gravitational effects are, of course, important on stellar scales. It is important, therefore, to account for these crucial features in a model for pulsars and these glitches that they exhibit. And so this is what we have done, and this has appeared in this paper recently. I've given you the reference. So what we do is we construct a minimal self-gravitating model. If you ask me enough questions, I will tell you why it is minimal for pulsar glitches. For this, we use the Gros-Pitayevsky-Poisson equation, GPPE, for a self-gravitating superfluid. First, for a non-rotating bosonic star, which we have studied earlier by this model. Then we include rotation, and then we also include a crust that interacts with the superfluid and the vortices therein. Let me tell you the results before I get into technicalities. What we find is that in the absence of the crust potential, if we rotate such a bosonic star, not surprisingly, it is threaded by vortices. And then we show by extensive direct numerical simulations, the details of which I will not give today, the interactions of these vortices with the crust potential yields A, stick-slip dynamics, and B, dynamical glitches. So within our model, we will have a precise definition of glitches. If the dynamics is such that enough angular momentum is transferred to the crust from the bosonic star, then the vortices are expelled from the star, and the crust's angular momentum J sub C exhibits features that may be interpreted as these glitches. From the time series of JC, now because we have very detailed data, we can compute the cumulative probability distribution functions of event sizes. I will define what these are, event durations, and waiting times. And we show that these CPDFs have the signatures of self-organized criticality, and these signatures have been observed in some pulsar glitches. All right, so this is why I included this talk, because Deepak has done so much for self-organized criticality. I thought he might be amused by this application. So here's the Gross-Pitaevsky-Poisson equation. All of you know psi is a complex wave function. So we are thinking of a bosonic superfluid, Cooper paired neutrons. And here's good old Gross-Pitaevsky. Here is the crust potential V of theta, which I will talk about presently. And here's the gravitational potential, which satisfies this Poisson equation. And for technical reasons, we have to subtract off the mean, etc. All right. So in the absence of gravity, this is just Gross-Pitaevsky, which we have studied a lot. And there is a speed of sound, coherence length, which sets the scale of the vortex diameter, and so on. And in the presence of gravity, this thing actually leads to a collapsed object, which you can interpret as the bosonic star, which we have done in this paper, which appeared about a year ago. So, but that's not what I'm going to talk to you about today. Today, I'm going to talk to you about the Gross-Pitaevsky-Poisson equation along with this crust potential V of theta. And we will assume that the crust dynamics is, well described at the simplest level by a single polar angle theta, which follows this equation. IC is the moment of inertia, so that's the double derivative of theta. Here's the term that comes from the potential. And then, because there is a frictional coupling between the crust and the superfluid, we have this coupling alpha del d theta by dt, and alpha controls the friction. The precise form of V naught, V theta, you don't need to look at, but it has built into it a crust, a typical crust diameter, and a crust width, and so on. And it is periodic, and so n crust over here in this periodic potential V tilde of x theta, y theta gives you the number of pinning sites in this crust potential. I'm sorry for some of these typographical errors. And so don't look at the details. Such a short talk is not meant for details. All I want to tell you is that the crust acts on the GPPE superfluid and also reacts to it. Now, in the absence of the crust potential, if you linearize about some constant wave function, then you do get a low K Jain's instability, the details of which are for some other talk. Let me skip that. Given this complicated Gross-Pitaevsky-Poisson equation with a crust potential, you have to go to a computer, and we know how to do that. And we use a pseudospectral method with suitable time marching and de-aliasing. Certainly, you're not interested in all that. And believe me, we conserve all the required quantities, the number of particles, and the energy, total energy, and the momentum if the crust potential is zero and the friction is zero. Now, this, for those of you who have looked at such things, this amounts to a microcanonical evolution of the Galerkin truncated Gross-Pitaevsky-Poisson equation. That evolution can take a lot of time, so at a technical level, it is useful to find the ground state by using an imaginary time variant, which is a stochastic Ginzburg-Landau-Poisson equation, which you can do at finite temperature. I won't do it here, but we do it in this work only at zero temperature. So the good thing about this imaginary time evolution is it helps us to find states with finite, minima at finite angular rotation frequency, which you will see buried here now. omega times Jz. So omega is the angular frequency of rotation for this whole assembly. Earlier studies had not managed to find these vortices threading this GPPE assembly, but because of this numerical cleverness, we could. You can find the angular momentum of the superfluid as a function of time. There's a minor decay with time because a cubical lattice doesn't have real rotational invariance. But you can find states without vortices. That's the straight line in red. And the green line actually has 4 vortices threading it. This is with the imaginary time dynamics. So you can see that we get, this is an isosurface plot of the density of curl of rho v squared actually. And you can see the vortices threading this assembly. This is without a crust. Now when we add a crust, you can see the vortices in blue and the crust potential in, crust potential in blue and the vortices in red. And as time progresses, because of the mechanisms that I had mentioned, occasionally one of these vortices gets thrown out.
2 more minutes, a gentle reminder.
I'll be done in 2 minutes. Thank you. Okay, so it's doing the right things. Then you can ask, well, how right is this thing? So you can ask for the crust potential as a function of time. And aside from the slight decay that I mentioned to you because of the lack of complete rotational invariance, it's as if not only does it fall, the crust potential, occasionally it exchanges angular momentum with the superfluid and the other way around. And in fact, there is a reciprocal relation between them. So here is what the time series looks like, okay? J crust versus time, and you see lots of glitches. And then if you blow it and zoom in, you can get this. And so you can actually define event sizes. So for example, delta JC would be the distance from one minimum to the next maximum. Then, T event would be between going from one minimum to one maximum. And for those of you who read cumulative probability distributions quickly, I will show you that these two, which are on log-log scales, show distinct power law regions, which is a sign of self-organized criticality. Waiting time distributions are exponential, but this is also true in the observations, which have seen such self-organized criticality in pulsar glitches, and new measurements promise to make even better data available so that we can, look at this more carefully. So I'm sorry for that very rapid talk, but here is a quick summary of our conclusions. We've shown that a uniformly rotating vortex containing gravitational bound solution of the GPPE can be generated by this imaginary time evolution. And then we have built on our earlier work, included a solid crust, and from it we can get the cumulative probability distribution functions of the event sizes and event durations, which show SOC type power laws. And these SOC type desiderata are in consonance with measurements in a class of pulsars. So with that, I thank you for your attention and happy 70th both to Deepak and to Mustansif. Thank you.
Thanks a lot for this interesting talk. The house is now open for questions.
Yes, Mustansif, please go ahead.
Yeah, Professor Burma.
Yeah, Rahul, maybe you said it in your last sentence, but a given pulsar, does it keep showing glitches?
Yeah, there are some pulsars don't show glitches, but some do. And now there are very good data.
Okay.
And they show this SOC. So SOC has been detected before we talked about it. It's not that we are the first to say.
I see.
We are the first to get it from a real semi-believable model.
Right. And so in terms of intermittency, are these intermittent, these glitches?
Well,
the time intermittent.
Yeah, I haven't checked in detail, will do so, but since the literature concentrated on SOC, that's what we did to begin with.
Yeah.
But yes, we could do higher order statistics, which of course we know how to do well. Yeah.
Okay.
Yeah.
So
Thank you.
one more question from Professor Abhishek Dhar.
Yeah, hi Rahul. So, I mean, it's sort of a general question. I mean, is it like, I mean, known that pulsars which have these glitches are have a superfluid core? I mean, is there some? I mean, why
Well,
does one?
known meaning nobody can go there.
Yeah,
right?
but how does one? Is there an independent like?
So this is a long history. Soon after these glitches came out, there was a model due to Pesach, Bain, Ruderman. Some people said star quakes. Other people, even Migdal had said in '59 that the inside would be superfluid. Now it's predominantly a neutron superfluid, but of course there are protons too, so they will form a superconducting assembly. And then, of course, you have to worry about the magnetic field, which we haven't put in. They will certainly affect the superconductor. And so we are planning to do all those calculations now. With that, of course, would be Ginsburg, Landau, Poisson, with electric field, etc., etc.
Okay, thanks.
So that's all that's known. I mean, the measurement is the glitches.
Right. Okay. Thanks.
Thank you, Professor, for this talk, wonderful talk.